Hello and a huge welcome back to all of you focused learners out there. I am absolutely thrilled to have you here for this explainer. Today, we're diving straight into one of the most massive engineering feats on the planet, the incredible structures that hold back literally millions of gallons of water just to power our modern world. That's right, we're looking at dams. We're going to break down exactly how these monolithic structures actually work, translating all that complex engineering into a really clear, visual journey.
Okay, so let's quickly look at our agenda for today. We'll kick things off with Section 1, the giant water battery. Next up, Section 2 looks at the anatomy of a dam. Then, in Section 3, we're going to uncover the physics of gravity at play. And finally, Section 4 covers the actual generation of hydroelectric power.
But before we get into the nuts and bolts of it all, I want you to really think about this for a second. How do you actually stop a river? I mean, it's a pretty provocative question, right? It really highlights the sheer, awe-inspiring scale of what human engineering is trying to achieve here. We're talking about intercepting the relentless, natural flow of the Earth's water cycle.
To answer that, we really have to start with a core definition. Fundamentally, a dam is a structure built right across a stream or a river to retain water or to act as a barrier that restricts or redirects the flow. And I absolutely want to emphasize those last two words, restriction and redirection. A dam isn't just a static wall sitting there. It's a highly dynamic tool of control.
All right, let's jump into Section 1, the giant water battery, storing potential energy.
So we kind of need to reframe how we look at that enormous body of water sitting behind the structure. It's not just a lake, it's a massive reservoir of stored energy just waiting to be unleashed. I really love this concept from FDE Hydro. Think of the reservoir not as a body of water, but as a giant battery. See, the sun causes evaporation, lifting water way up into the atmosphere, which then falls as rain and collects in the river basin. The dam captures that water at an elevation, so essentially, the reservoir stores potential energy at a height rather than storing chemical energy like, say, the AA batteries in your TV remote. Hydropower, in a way, is honestly just solar energy wearing a raincoat.
Moving on to Section 2, Anatomy of a Dam, the blueprint. Now that we understand why we hold the water back, let's look at the how. Let's break down the universal components of these massive structures so we can truly grasp the physical blueprint. Because every single component here plays a vital role in maintaining decades of stability. You've got the crest up at the very top. Down at the foundation, the heel is the contact point on the upstream side, where the water actually is, and the toe is the contact point on the downstream side. For safety and maintenance, we have the spillway to release excess water so the dam doesn't overflow, the sluiceway to clear out built-up silt near the ground level, and drainage galleries. Those are essentially small rooms and tunnels left right inside the dam for inspection and managing internal water seepage.
Notice how the heel and toe brilliantly anchor the entire structure to the earth. You can also clearly see the galleries situated internally, while the spillway and sluiceway provide calculated paths through or over the massive concrete block relative to the normal and maximum water levels.
And just look at the extreme difference in the slopes here. The upstream face, the side actually touching the deep water, is often nearly vertical. But check out the sheer slope of the downstream face. It creates this incredibly wide, heavy base. Now, this isn't just for aesthetics. It's a very specific, carefully calculated design used to manage the immense hydraulic height of the water pressing constantly against it.
Which brings us to Section 3, the physics of gravity, standing still against nature. This is where the structural mathematics truly come alive. Inside all that concrete, there's this invisible push and pull battle of forces happening every single second. A gravity dam has a beautifully simple survival strategy. You have incredible destabilizing forces, right? Upstream water pressure trying to push it over, uplift pressure from water seeping underneath trying to lift it, plus waves, wind, and even earthquakes. So how does the dam fight back? With massive stabilizing force, its own self-weight. It literally survives simply by being so incredibly heavy that the water just cannot move it.
The absolute crucial point here is understanding how that water pushes. Notice how the water pressure forms a triangular load. The pressure is zero up at the very top of the reservoir. But as you go deeper, the sheer weight of the water above increases the pressure. By the time you reach the very bottom, that pressure is at its maximum. This creates a massive, wedge-shaped horizontal force constantly shoving against the concrete.
And the engineers have to calculate every single drop of this. They account for that massive triangular pressure from the upstream water
and even the smaller counterpressure from the shallow tailwater downstream. They also have to calculate the uplift pressure pushing from beneath. To keep the whole thing standing, engineers use math to ensure that the ultimate resulting force of all this intense pushing and pulling stays safely directed right into the middle third of the dam's base. Because, if they get those calculations wrong, the results are completely catastrophic. Here are the 4 main ways a gravity dam can fail. Sliding is when those horizontal forces are so overwhelmingly great that they simply shove the dam right along the foundation. Overturning is when the water literally tips the entire massive structure over. Crushing happens if the concrete just gives way and shatters under the extreme compression of its own immense weight. And tension occurs when stretching forces violently crack the structure wide open. This is exactly why engineers build in a factor of safety between 4 and 5, meaning the dam is engineered to be up to 5 times stronger than it theoretically even needs to be.
Let's dive into Section 4, Generating Hydroelectric Power, from Potential to Kinetic. So, we're transitioning now from looking at the dam as a static, heavy wall to seeing it as a highly dynamic electricity generator. I really want you to read this quote from Bill French, senior over at FDE Hydro. Gravity does the heavy lifting. It is just such a profound summary. The dam doesn't actually create energy. It just controls when and how fast the water falls. The natural pull of gravity on that elevated water is the true engine of the entire operation. So here is the really punchy cause and effect narrative of how that gravity becomes the electricity powering your wall outlet. Step 1. The water sits quietly in the reservoir as potential energy. Step 2. Intake gates open and water rushes downward through a large, highly pressurized pipe called a penstock, immediately converting to moving kinetic energy. Step 3. That pressurized water slams right into a turbine, spinning its blades and creating mechanical energy. And finally, Step 4. That spinning turbine drives a generator, which gives us electrical energy.
I do want to make a really clear distinction here, though. The turbine itself does not make electricity. It makes rotation. When the water turns the turbine, a connecting shaft spins a component called a rotor inside the generator. And this rotor spins inside a stationary ring of copper wire, which we call a stator. It is that physical, mechanical motion, literally spinning magnets inside copper wire, that converts the mechanical energy directly into the flow of electricity we rely on every single day.
Which brings us to the end of our explainer. I want to leave you with this final thought. When you flip a switch in your house tonight, will you picture it? Will you picture the immense, silent battle of forces, millions of tons of concrete fighting a wedge of pressurized water, all working perfectly in sync with gravity and spinning turbines, just to power your home? It truly is an unbelievable piece of infrastructure. Thank you so much for joining me on this deep dive. Keep learning, and I will catch you on the next explainer.